This lecture looks at evaluating the Solow growth model with exogenous technological growth. So this is one of the versions where we will get a result of GDP per capita increasing, and we want to see the mechanism through which that happens. So this is exogenous technological growth. It's not an endogenous growth model. It is just a constant rate of tech growth assumed exogenously from the outside. Our key metric in evaluating these Solow growth models is, does it generate steady state real GDP growth per capita, which we're going to measure as GDP per worker, but we could use the total population as well, which is the technical definition of GDP per capita, hence the capita. The assumptions in this model is that we will have technological growth, so we can change that. And we're going to assume A hat is just growing at some rate G that's positive. G could be a number, 2%, 3%, whatever you like, but it's just going to be a constant growth rate generating new technology. Now, we remember technology is going to allow us to produce more per capital and per worker, and so it's really going to be the key to generating technological growth in GDP per capita in the long run. We're going to assume, for simplicity, that there's no population growth. It won't matter because it doesn't generate this, but it's easier if we just assume it's zero, which means also that is the growth rate of the labor supply. So let's go through our basic steps. Step one is to use the definition of steady state, which here is that the change in capital per labor is zero. That's the definition of steady state, so I put a little symbol there. We now use the definition of capital per worker, convert that to growth rates. That's a little k. This tells us that this has to be 0 too. So if I were to draw a line, that's where that comes from. By assumption, this is 0. So if that's 0 and those two have to be add up to 0, or k minus L hat have to be minus 0, then k also is 0. Again, if I graph this, I would get log of L is a constant, log of capital, and I'll drop the log sign here. It's there, they're logs. These two are constant, so K over L must also be constant. This is no change, which is why we get that. Now, step two uses the production function, and we look at production in this economy. It's K alpha. The A is right in there, and since it's growing, this is going to be growing. So when we convert it to growth rates, we find this, by definition, is growing at 0. So these two must be growing at the same rate. So we have that GDP per capita, per worker, is growing at the same rate as technology, which is the growth rate G. Now we can look at GDP per capita and see what's driving it. And you'll see why we do step 3. GDP per capita or per labor. This again is our goal to answer this question up here, and we see, by definition, GDP per worker, when we convert it to growth rates, we know by assumption there's 0 population growth, so this is 0 by assumption of no growth rate. This, we know from here, is growing at G. We know that. So this is 0, and this is still here, so we know this is growing at G. What's happening here? Total GDP is growing at a rate of G. Labor is constant. So when I take this that's growing and divide it by something that's constant, we get this growing at a rate of G, which means this is growing at a rate of G, and we've answered yes. Real GDP per capita is growing at a rate of technological progress. We can see that here.